All right, today we're tackling a really powerful method for solving systems of linear equations. It's called Cramer's rule, and it's a super slick, formula-based tool to have in your back pocket. So let's just dive right in. You know how it is. Sometimes you're wrestling with substitution or elimination, and you just get lost in this huge mess of variables. It can be a real headache. Well, Cramer's rule is kind of the answer to that. It's a much more direct, almost plug-and-play approach that gives you a clear path to the solution every time. So if you're tired of that mess, you're going to love this. So here's the game plan. First, we'll cover what the rule actually is. Then we'll jump into a simple 2x2 system. We'll do a full example together, see how this whole idea scales up to bigger systems, and then I'll give you a chance to try it out for yourself. Okay, first things first. What in the world is Cramer's rule? Let's break it down. At its heart, Cramer's rule is a specific recipe. And like any good recipe, it has one key ingredient that makes the whole thing work. In this case, that secret ingredient is something called a determinant. And, that brings us to a really crucial point. This whole method is built on determinants, that single number you calculate from a square matrix. So if you're a little fuzzy on how to find one, this might be a good time to hit pause and do a quick refresh, because trust me, we're about to use them a lot. Let's kick things off with the most common setup you'll see: two equations and two variables we need to find, x and y. This is really the foundation of the method, and it's the perfect place to see how elegant it is. So here's the general layout of any 2x2 system. The numbers in front of our variables, the a's and b's, those are our coefficients. And the numbers all by themselves on the other side of the equal sign, the d's, those are the constants. You'll want to keep an eye on this structure because where each of these pieces goes is literally the key to the whole thing. And bam, here are the formulas. As you can see, to find x or y, you're just calculating a fraction made of two determinants. But what's really cool is the pattern. Look at the denominator. It's the exact same for both x and y. It's always the determinant of the original coefficients. The real magic happens in the numerator. To solve for x, you just take the x coefficient column and replace it with the constants. To solve for y, you guessed it, you do the same thing for the y coefficient column. It's just a simple, repeatable pattern. So the entire process really just boils down to these four simple steps. First, get that main determinant from the coefficients. That's your denominator. Then, you calculate the two special determinants for the top parts. And finally, you just divide. That's it. That's the whole shebang. Okay, theory's one thing, but let's see how this actually works with some real numbers. There's no better way to learn than by doing, right? Here's our system. We've got our coefficients, 3, 4, -2, and -3, and our constants, -14 and 11. Now it's time to just plug them into our formulas. First up, let's solve for x. You can see the denominator is the determinant of our original coefficients, just like we said. And for the numerator, we've swapped out that first column, the x coefficients, with our constants. Now let's just crunch the numbers. When you calculate the determinant on top, you get -2. The determinant on the bottom works out to be -1. So -2 divided by -1 gives us our answer for x, a nice, clean 2. Now let's do del u. And the beauty here is that we've already done half the work. That denominator is the same one we just calculated, -1. So all we have to do is find the new numerator, where we've swapped the y coefficients with the constants. The top determinant here comes out to 5. We divide that by our denominator of -1, and we get our solution for y. It's -5. And there we have it. The solution to our system is x equals 2, y equals -5. See how direct that was? No messy rearranging. And you can even plug these numbers back into the original equations just to be sure, and you'll see they work perfectly. So you might be wondering, does this neat little trick work for bigger systems? And the answer is absolutely. Let's take a quick look at how the same logic applies when we throw a third variable, z, into the mix. Now, when you've got 3 equations and 3 unknowns, it might look a little more intimidating at first glance, but trust me, the fundamental pattern behind Cramer's rule stays exactly the same. See? It's the same idea, just bigger. The denominator for all 3 variables is the big 3x3 determinant of all the coefficients. Then, to solve for x, you replace the first column with the constants. For y, you replace the second column. And for z, you replace the third. It's that same beautiful, consistent pattern. All right, you've seen the theory, you've seen an example worked out, now it's your turn. Time to put this new knowledge to the test. Seriously, the best way to make sure this all makes sense is to do it yourself, so go ahead and grab a pen and some paper. Here are two problems for you. The first one's a classic 2x2, and the second is a 3x3 to really test your skills. Go ahead and hit pause, apply Cramer's rule, and see what answers you come up with. I'll be here when you get back. Okay, you ready to check your work? For the first problem, you should have gotten x equals 3 and y equals -2. And for that bigger 3x3 system, the answer is x equals 1, y equals 2, and z equals 4. So, how'd you do? And we'll finish up with a little something to think about. We've been dividing by that main determinant this whole time, right? But what happens if that determinant works out to be 0? I mean, you can't divide by 0, so what does that tell us about the equations themselves? Does it mean there's no solution? Or maybe something else entirely? That is a fantastic question to dig into next. Thanks so much for watching,